In the world of aircraft engine technology, innovation is often the key to gaining an advantage in battle. One of the most notable examples of such innovation is the inverted V12 engine produced by Daimler-Benz. Known for its unique design, with a crankshaft on top and pistons along with all cylinder head components positioned below, this engine was not merely a propulsion device, but also a remarkable engineering achievement that significantly impacted German military tactics and strategy during World War II. The question is, why was this engine designed to be inverted? And what advantages were gained from this unconventional design? In this discussion, we will explore the history, innovations, and impact of the Daimler-Benz inverted V12 engine, while uncovering why this design remains relevant and influential to this day. In the 1930s, Germany had a pressing need for aircraft engines capable of producing more than 800 horsepower, while still maintaining a highly compact cooling system to reduce aerodynamic drag. They required an engine that could operate efficiently on low-quality fuel, be easily repairable, and allow the installation of machine guns at the front of the aircraft to improve firing accuracy, aligned with the pilot's line of sight. The DB600 engine was Daimler-Benz's answer to the challenge. One of its key innovations was the use of the duralumin, a blend of aluminium, magnesium, and copper. This material was not only extremely lightweight, but also had excellent thermal conductivity, allowing heat generated by the combustion system to dissipate evenly throughout the engine. The inverted design also enabled the pistons to be optimally lubricated, as gravity pulled the oil downward, cooling the pistons more effectively compared to conventional engine designs. In addition, the DB600 engine cylinders are equipped with liners containing silicon, which provide better wear resistance and extend the cylinder's lifespan, even under heavy operating conditions. Furthermore, in an inverted position, the oil flows to the bottom of the piston, providing efficient cooling, similar to the oil injection systems found in modern engines. Now, the pistons in this engine are made from lightweight alloy materials. With their inverted position, a diameter of 150 millimeters, and a stroke of 160 millimeters, these pistons require 5 rings. 3 rings are used for compression, while the other 2 function as oil scrapers. The question is, why 5 rings? This is necessary to ensure that oil does not enter the combustion chamber, as oil passing through the rings and burning would certainly disrupt engine performance. And here, there is one important thing to note. If the engine is left unused for an extended period, oil can seep down and flood the cylinder. In such situations, the spark plugs must be removed and cleaned before the engine can be started again. Moreover, the bottom ring has an additional function. This ring helps keep the piston centered within the cylinder. Without this support, the piston could shift and create a pitching effect, or unstable up and down motion. As a result, the engine becomes noisier and component wear increases. This engine has a displacement of 33.9 liters, with a fuel capacity of 9 liters or approximately 2,070 cubic inches. If we calculate it, each cylinder of the DB600 has a capacity of 2.8 liters. Additionally, the engine is equipped with a supercharger, which was initially driven by a shaft directly connected to the crankshaft. The main function of the supercharger is to increase power during takeoff and maintain performance at high altitudes, where the air becomes thinner and the engine lacks sufficient oxygen. With this large displacement and the assistance of the supercharger, the DB600 engine is capable of producing up to 1,000 horsepower at 2,800 RPM, despite weighing less than 700 kilograms or about 1,500 pounds. For piston support, if we observe closely, this engine uses a fork and blade connecting rod configuration mounted on the same crank pin. This means one rod is positioned on the inside, while the other is on the outside. Such a configuration ensures perfect cylinder alignment and eliminates additional vibrations, uneven wear, and efficiency losses, which are commonly found in engines with side-by-side connecting rods. To enhance reliability, this engine uses needle roller bearings, which allow for short-term operation without oil and enable the pilot to return to base in case of lubrication failure. Additionally, the inverted position of the piston provides another advantage, as it remains lubricated by residual oil. The Daimler-Benz 600 engine was designed with an initial compression ratio of 6.9 to 1. This ratio was efficient enough to meet the aviation demands of its time, providing a good balance between power and reliability. As part of the redundancy system standard in aviation, each cylinder was equipped with 2 spark plugs. Each spark plug was powered by an independent magneto, ensuring that if one magneto failed, the engine could still operate, albeit with a slight reduction in power. The large cylinders in this engine required 2 spark plugs to ensure complete and timely fuel combustion. Ideally, these spark plugs would be placed opposite each other to improve combustion efficiency. However, due to space limitations and the presence of injectors, both spark plugs had to be mounted on the same side. The engine's lubrication system uses a dry sump design. The valve covers not only serve to protect internal components, but also function as oil reservoirs. Additionally, each cover is equipped with an oil pump that circulates the fluid to the main tank where the pressure pump is located. This system allows the engine to operate in any position as long as there is oil in the pressure tank. Next, the camshaft is positioned in the valve cover area and driven by gears. This design allows the camshaft to connect with the oil pump as well as the shaft that drives the compressor. The compressor is also directly linked to the crankshaft, ensuring synchronization and efficiency of the entire mechanical system. Each side of the engine is equipped with a camshaft that rotates at half the speed of the crankshaft. The camshaft operates 2 intake valves and 2 exhaust valves for each cylinder. To maintain rotational synchronization, the camshaft gears are designed to rotate in opposite directions. One rotates normally, while the other rotates in reverse. This design ensures that all components work harmoniously, providing high reliability and efficiency for the engine. This inverted engine design is not only innovative but also offers significant practical advantages. One of the main benefits is the placement of the exhaust pipes at the bottom. With this configuration, any oil that might exit through the exhaust will not stain the windshield, ensuring clear visibility during flight. Additionally, the placement of the exhaust pipes at the bottom helps reduce the glare produced by the exhaust flames, especially during night flights, allowing the pilot to maintain optimal visibility without distractions. The inverted engine design, where the crankshaft output is positioned at the top, provides another significant advantage. This configuration allows for the installation of reduction gears that lower the propeller's speed. As we mentioned earlier, the engine can spin at up to 2,800 RPM, while the propeller rotates at only 1,700 RPM. This lower propeller speed is crucial to prevent the propeller tips from exceeding the speed of sound, which could cause aerodynamic disturbances and reduce flight efficiency. Furthermore, this engine design is crafted with accessibility and maintenance in mind. The spark plug placement and maintenance system are designed to be easily accessible by mechanics, simplifying inspection and component replacement processes. This configuration also creates extra space for mounting machine guns directly within the pilot's line of sight. This strategic placement offers a significant advantage in improving shooting accuracy during aerial combat. Uniquely, these guns can be fired through the center of the spinning propeller thanks to an advanced synchronization mechanism. This system is designed to ensure that the bullets pass cleanly between the propeller blades, preventing damage to the propeller and maintaining efficiency and safety during combat operations. The V-shaped engine configuration provides substantial benefits for weapon placement. At the rear of the engine, there is a dedicated space for mounting a 30mm Mk108 cannon. Additionally, at the front, there is room for smaller caliber weaponry, such as a 20mm cannon. Placing weapons along the aircraft's center line offers several advantages. When the weapons fire, the recoil is absorbed directly by the aircraft's main frame, significantly reducing vibrations and ensuring stability, which in turn enhances overall firing accuracy. Conversely, wing-mounted weapons tend to face more challenges. Vibrations caused by high G maneuvers during aerial combat can compromise the precision of the shots. Furthermore, the flexing of the wings due to aerodynamic pressure can lead to reduced weapon accuracy. To address these issues, the integrated design of the engine and armament provides a more efficient solution. Two smaller machine guns are mounted on the top of the aircraft's fuselage and synchronized with the propeller using a high-precision mechanism. This system ensures that bullets fired do not hit the spinning propeller, maintaining the optimal performance of both the weapons and the aircraft components. The design of this reverse engine offers an additional benefit in maintaining the aircraft's center of gravity. With a better center of gravity, the aircraft's stability significantly improves, making it easier to maneuver, especially in intense combat conditions. Another important aspect that was a primary concern in the development of this engine is the efficiency of its cooling system. Unlike modern car engines, which operate at around 195 degrees Fahrenheit or 90 degrees Celsius, this engine is designed to operate at much higher temperatures, specifically 250 degrees Fahrenheit or 120 degrees Celsius. The increase in operating temperature creates a larger temperature difference between the outside air and the radiator, allowing the radiator to work more efficiently, even though its size is reduced by almost half of the original size. The advantage of reducing the radiator size is highly significant. With a smaller radiator, the aircraft's aerodynamics improve, the overall weight is reduced, and fuel consumption can be optimized because less coolant water is needed. However, operating at high temperatures brings new challenges. Naturally, water boils at 212 degrees Fahrenheit or 100 degrees Celsius under standard atmospheric pressure. To prevent the formation of steam at 250 degrees Fahrenheit or 120 degrees Celsius, the cooling system is designed to be closed and its pressure is increased. By raising the pressure, the boiling point of water increases, allowing the system to operate at higher temperatures without causing the water to boil. Nevertheless, increasing pressure presents its own risks. The system must be designed to be much stronger to withstand the high pressure, as even the smallest weakness can lead to a total failure. If there is a leak or damage due to gunfire, the pressure in the cooling circuit will drop drastically. Under such conditions, the high-temperature coolant will immediately vaporize, almost certainly causing catastrophic engine damage. Despite efforts to increase the operating temperature to 250 degrees Fahrenheit, the results were unsatisfactory. Therefore, the engine's operating temperature was lowered back to around 212 degrees Fahrenheit. However, operating at high temperatures introduced another problem, especially in the first DB600 engine that used a carburetor. This system was known for its reliability, but Germany faced a significant challenge in producing high-quality, high-octane fuel. This high temperature only exacerbated the risk of knocking, which is the uncontrolled expansion process inside the combustion chamber, potentially causing direct engine damage. To address this issue, the initial solution applied was to lower the engine's compression ratio. While this reduced the risk of knocking, it also sacrificed power and increased fuel consumption, which became a challenge for the operational efficiency of the aircraft. In addition to the Bf-109, the DB600 engine was also used on the Messerschmitt Bf-110, a heavy fighter aircraft that served as a long-range interceptor and night bomber. The DB600 engine provided powerful thrust for the Bf-110, despite the aircraft being heavier compared to lighter fighters like the Bf-109. The engine's strength enabled the Bf-110 to effectively carry out long-range missions. Another fighter aircraft using the DB600 variant was the Heinkel HE-111, a medium bomber that played a crucial role in Germany's Blitzkrieg campaign. With the DB600 engine, the HE-111 was capable of carrying large bomb loads while maintaining enough speed to evade enemy aircraft attacks. This engine gave the HE-111 ideal capabilities as a tactical bomber. In 1935, the DB601 engine was officially introduced, bringing a major innovation to aviation with a mechanical direct fuel injection system developed by Bosch. This direct injection system was a truly revolutionary technological breakthrough. Unlike the diesel injection system commonly used at the time, gasoline has far more aggressive properties. Gasoline can damage seals and O-rings on pumps, and lacks the lubricating properties of diesel, making pump components more prone to wear. To address this challenge, Bosch designed a highly advanced injection pump, kept secret as a national security measure. The injection pump used 12 inline pistons capable of generating fuel pressure up to 90 bar, injecting it directly into the combustion chamber. However, this technology was not without its problems. During early development, the fuel spray often hit the cylinder liner, disturbing lubrication and increasing friction. This issue was eventually solved with special nozzles that produced a wider fuel spray, along with support from an additional oil system on the reverse engine. Direct injection provided many significant benefits. When liquid fuel is injected into the cylinder, it immediately vaporizes, absorbing a large amount of heat and lowering the combustion chamber temperature. This process helps prevent knocking, allowing the engine to use lower-octane fuel that was more easily available in Germany without sacrificing performance. This technology also enabled aircraft to operate in extreme conditions, such as prolonged vertical maneuvers or even flying inverted, something that was impossible with conventional carburetors, as their floats would run out of fuel. In addition, the latest version of this engine was equipped with a hydraulically operated supercharger. Gears connected to the crankshaft drive a torque converter, which automatically adjusts the amount of oil inside according to the aircraft's altitude. As a result, the supercharger speed can be optimally adjusted. As the aircraft ascends to higher altitudes where air and oxygen become thinner, this supercharger ensures that the airflow remains sufficient. With a compressor pressure of about 20 psi, the DB601 engine could produce up to 1,300 horsepower at 2,600 RPM. In fact, for short-term operations, this engine supported nitrous oxide injection, or a water-methanol mixture, which could increase the power to 2,300 horsepower. This technology was particularly helpful, especially when escaping enemy fighter interceptors. In addition, we will find the DB603, an improvement over the previous series with higher power and efficiency, used on the Dornier Du 217. This aircraft was a long-range bomber frequently tasked with heavy bombing missions over England and other Allied territories. With greater power from the DB603 engine, the DO 217 was able to carry a larger bomb load and fly longer distances, making it a significant threat in long-range aerial combat. Manufacturers like Fiat in Italy and Kawasaki in Japan received the DB601 engine blueprint to support the development of their respective fighter aircraft. From this design, the DB605 was born, an advanced version with several significant improvements. The DB605 engine is an inverted V12 configuration designed to produce a maximum power output of up to 1,475 horsepower or 1,100 kilowatts at sea level, particularly when using emergency power mode. With this engine, the Messerschmitt Bf 109 fighter aircraft was capable of reaching a top speed of up to 643.7 kilometers per hour in level flight. This speed could even increase to 749.95 kilometers per hour when diving sharply, though this speed posed a risk of instability to the aircraft's structure. The DB605 had an increased engine capacity of 35.7 liters, and at takeoff, it could produce up to 1,475 horsepower. However, when using high-octane fuel, its maximum power could rise to 1,800 horsepower. To support this performance, the compression ratio on both banks of cylinders was designed differently. The right bank had a compression ratio of 7.3 to 1, while the left bank, where the compressor was located, had a compression ratio of 7.5 to 1. The reason for this difference was to counter the knocking issues that occurred more frequently on the left bank. The cause was the direction of the crankshaft's rotation, where more oil tended to fall onto the left bank, which then entered the combustion chamber and could potentially cause knocking. By lowering the compression ratio on this side, the issue was successfully addressed. The DB605 engine was equipped with an active cooling system to counter the potential overheating from this high power. Two radiators were placed beneath the wings, near the wing roots, connected to two main metal tanks on the sides of the engine. This system used a mixture of water and glycol flowing through the radiators to lower the fluid temperature before it returned to the engine, maintaining the engine's optimal temperature. To maintain power consistency, The DB605 was also equipped with an automatic supercharger, which compressed the air before sending it into the cylinders, increasing thrust when needed, especially during intense aerial combat. This supercharger received air from the side air intakes and compressed it through a 16-blade centrifugal impeller. Additionally, there was another major change in the engine design, which was the replacement of roller bearings with regular bearings to improve the engine's long-term reliability. The DB605 engine operated at a maximum of 2,800 RPM for short periods, while the standard operating speed was around 2,300 RPM, providing continuous power of 1,080 horsepower or 805 kWh. The 2.99-meter diameter metal propeller was equipped with an automatic pitch adjustment mechanism, reducing the pilot's workload during combat. After discussing the design and advantages of the DB605 engine, we now move on to the more advanced and powerful version, the DB610. The DB610, a combination of two DB605 engines, offered incredible power, but its compact design made maintenance a challenge. This engine was used on the Heinkel HE-177 long-range bomber with a combined capacity of 71 liters, which can technically be considered a W24 engine. The DB610 was capable of producing up to 2,900 horsepower, providing the immense thrust needed for long-range bombing missions. However, its maintenance was quite complicated. For example, to replace the spark plugs in the inner cylinders, mechanics had to disassemble the exhaust manifold first, which even required removing one of the engines from the aircraft. The advanced technology embedded in the DB605 engine gave German aircraft, such as the Bf-109, a significant advantage in combat, enabling them to compete effectively in aerial battles and make a substantial contribution to the Luftwaffe's strength during World War II. The Daimler-Benz V12 engines, such as the DB600 and its variants, are often compared to the Rolls-Royce Merlin engines that powered Allied fighter planes like the Spitfire and P-51 Mustang. One of the key differences between them lies in the direct fuel injection technology used by the DB600. This injection system allowed the engine to deliver a stable fuel supply even during extreme maneuvers, such as inverted flight or vertical climbs. With this technology, German aircraft could maintain full power without the sudden fuel starvation risk that typically occurred with carburetor-based engines. In contrast, the Rolls-Royce Merlin engine still relied on a carburetor to mix fuel and air, making it prone to power loss when the aircraft operated in extreme positions. As a result, pilots of Merlin-powered aircraft might experience performance limitations during sharp climbs or dives, a drawback that German pilots could exploit in aerial combat. This technological difference provided German fighters with a tactical advantage in certain situations, particularly in maneuvers that demanded the engine's endurance and responsiveness under extreme conditions. In addition to outperforming the Spitfire and P-51 Mustang, these engines helped German aircraft surpass many other fighters, including the Hawker Hurricane, P-40 Warhawk in altitude and speed, as well as Soviet aircraft like the Yakovlev Yak-1, Yak-3, Yak-7, and Yak-9, the Curtiss P-36 Hawk, the Bell P-39 Airacobra, and the Polikarpov I-16. The inverted Daimler-Benz VI-12 engine not only brought innovation during its time, but also influenced aircraft engine designs after the war. Although the concept of the inverted engine was not widely adopted in aircraft design following World War II, many other technologies, such as direct fuel injection and more efficient cooling systems, continued to be developed and utilized in modern engines, both in aviation and the automotive industry. The impact of this design can also be seen in how modern engines consider weight distribution to maintain balance and maneuverability, particularly in high-performance vehicles. In wartime situations, quick and effective maintenance becomes crucial to maintaining the performance of combat aircraft. One of the biggest challenges faced by technicians was changing the spark plugs, which were difficult to reach due to the inverted engine configuration. This required extra precision, and during intense combat, the time for repairs was very limited. To address this issue, German technicians developed more efficient maintenance procedures and used special tools to facilitate spark plug replacement in the field. The durability and speed of this maintenance became one of the reasons the DB600 engine remained the primary choice in many German fighter aircraft, despite some weaknesses in its design. The DB600 engine demonstrated extraordinary toughness in the battlefield, but several issues, such as oil leaks related to the inverted design and maintenance complexity, remained a challenge for technicians. In particular, the difficulty of replacing spark plugs in some configurations could delay repair speed. However, the application of needle roller bearings in this engine helped improve durability and reduce internal friction, contributing to the long-term reliability of the engine. With innovation and adaptation in maintenance procedures, the DB600 engine was able to withstand extreme battlefield conditions, keeping German fighter aircraft in the advantage. The inverted Daimler-Benz V12 engine not only brought changes in technical design, but also influenced how German aircraft operated in aerial combat. One of the most famous moments highlighting the advantage of this engine was during the Battle of Britain. German pilots flying the Messerschmitt Bf 109 were often able to perform extreme maneuvers, such as flying inverted or climbing steeply without losing engine power, an ability difficult for Allied aircraft, which still used carburetor engines. When Allied aircraft performed sharp vertical climbs, the Rolls-Royce Merlin engine often experienced fuel starvation due to the carburetor's inability to adapt to the changing angles of the aircraft. On the other hand, the DB600 engine, with its direct fuel injection system, continued to operate optimally, giving German pilots a significant advantage to keep pressing their opponents in the air. In conclusion, the inverted Daimler-Benz A312 engine was not just an example of technological innovation for its time, but also a symbol of the synergy between military needs and the creativity of engineers who created strategic advantages. With various innovations, such as an efficient cooling system and direct fuel injection, this engine left an indelible mark on the history of military aviation. However, the question remains: how can innovations in past engine designs influence future engine technologies? Will we see similar principles applied in modern land or air vehicles? We'd love to hear your thoughts. Do you think innovative engine designs like the Daimler-Benz V12 are still relevant for modern transportation technologies? Or perhaps you believe there are other innovations that are more important? Write your comments below and let's discuss further. Thank you for watching our video, and we'll see you in the next one.